Hello and welcome to lesson 2 of our trigonometry chapter. This will pick up exactly where we left off in our last task, talking about the Ferris wheel and its height above the ground at different positions while our friend Carlos was riding it. Some facts about our work in our last video are listed in front of us now. We know that the Ferris wheel had a radius of 25 feet. So we knew that anywhere this length right here was going to be 25, and that's all the way around the circle for any of these spokes of the wheel. The center of the Ferris wheel is 30 feet off the ground, so that was this distance right here. And we see some of our work for point B in front of us. So we knew that the 10 sections were divided up. We can do 36-degree segments. And if this was x, we could set up a sine function for this to figure out the height above the middle of the Ferris wheel. So the way we did that last time, if you forget, was the sine of 36 was going to be equal to x over 25, like so. And that meant that 25 times the sine of 36 gave us x. And then in order to figure out the height of B, we would just do the 30 feet that the center is above the ground plus this value. So it would end up being 30 plus 25 sine of 36. And if you were actually to find those values, that would end up being 30 plus that's 25 sine of 36. So it'd be 30 plus 14.7 in other terms. And that meant that point B in this particular example was 44.7 feet off the ground. Now, this is all well and good, but normally when you're thinking about like something like this, the height off the ground, you're not going to think, well, how many degrees around the circle have I gone? Maybe if you're riding a carnival ride like a Ferris wheel, you might be thinking of, well, how long have I been on the ride for from when I'm starting at position A? If I know how many seconds have elapsed, I'd be able to know what height off the ground I would be. And that's where Carlos took our task next. He, from the ground or from his ride in it, kind of depends on what time during this it was going on. So he made one complete revolution counterclockwise every 20 seconds. A note in general that if you're talking about trigonometry, normally kind of positive degrees, or in this case, positive carnival ride would be in a counterclockwise direction. So that's just something to file away later. Counterclockwise is always going to be positive. So just keep that in mind. So our first question asks us, how high will Carlos be 2 seconds after passing position A on the diagram? So if position A is 0 seconds, we want to know after 2 seconds how far would he have gone. So that's something we can look at and think about a topic called angular velocity, angular speed. In this case, angular velocity. So I'll have a video for you guys, hopefully to watch before you start this, on what angular velocity is, but it's basically how many degrees per second you are moving through. So if they make one complete counterclockwise every 20 seconds, that means that we have 360 degrees in 20 seconds. If I divide 360 by 20, that means I have 18 degrees in every 1 second. So that's going to be important for finding how high you're going to be at any given time, because now we know, well, what the angle is going to make, and use the same strategy we learned last lesson. So using that information, if we know that we're talking about 2 seconds, for instance, so I could do 2 seconds times 18 degrees, and that gives me 36 seconds. And so that basically gives us right there what we kind of worked on from before. So if I knew 2 seconds in would be the 36 degrees that we have here, and so I know that I did the 25 times sine of this input of 36 seconds instead of 36 degrees. So 2 seconds and 36 degrees would basically be the same thing, is what we're basically saying here. So our answer from before, 44.7, would go with 2 seconds. So we have figured that part out. So something that might be helpful if we look on the back of our page, we can see we have lots of different amounts of seconds that we're going to be looking at. And we're going to try to see, well, how can I find the height of any one of these and figure out how high on the rider would be. So now if we are thinking about the actual Ferris wheel here, so if we knew that the whole thing was going to be 20 seconds and we're going at 18 degrees per second, so that means that we could label this as 5 seconds would be a quarter turn, or a quarter of 20, and then we'd have 10 seconds for 3/4 of or half a turn. We'd have 15 seconds for 3/4 of a turn, and we'd have 20 seconds, which we already knew, for an entire turn. So anything between 0 and 5 seconds, we'd be able to use our first quadrant to find those heights. So now, continuing onwards, if we are going to try to start filling out our table on the back, we can see we need 1 second, 2 seconds, 2.5, 3, etc., etc. So now we're going to use some scratch paper to look at how we can find it within the first quadrant. Will be these first 4 rows of the table, and then we know that 10 seconds would be 6 and 8 in the second quadrant, and then our 14.5 would be the third quadrant, and then 18 all the way. So 18 would be the fourth quadrant, and then 23 and up would be after a whole revolution has already passed. So we're going to look and see at the first quadrant first and see like 1, 2.5, and 3 seconds. So we're going to do that on some scrap paper. So our first circle that we're going to draw, this is our Ferris wheel, and we have point A where our ride is starting. So if we know we're going to be doing 1 second, 1 second, that is going to be 18 degrees. So because we know that it is 18 degrees per second. So keep that in mind when we keep doing this. So if I know I have 18 degrees, I could draw a line right here. So this is my new position after 1 second. I've gone through 18 degrees. And just like before, I can draw my line downwards to create a right angle right there. And I know that this hypotenuse, the radius of our Ferris wheel, is always 25. And I know that this distance is 30 feet. And so now I can find my x value. So like similar to before, I'm going to do the sine of 18 is going to be equal to x over 25. And so now we have the 25 times sine of 18 is that x height. And we just need to do 30 plus 25 sine of 18. And that would give us our answer for height after 1 second. Will be just 18 times 1 second. 18 times 1 second would be 18 degrees. So if we 30 plus 25 sine of 18 degrees would be 37.7 feet off the ground. So that's pretty simple so far. So we already did 2 seconds, so let's look at 2.5 seconds. So now if we have 2.5 seconds, and we multiply that by 18 degrees per second, our rate. So if we multiply that, 2.5 times 18 degrees per second, that is giving us 45 degrees. So that would be kind of in between here. And it's going to be basically the same process. So we'd end up with that 45 degrees where that is there. So we now have 30 plus 25, a sine of 45 degrees. And we could enter that into our calculator. 30 plus 25 sine of 45 degrees. That is 47.7 feet off the ground. So higher than what we were before. So then, kind of last for this quadrant, we could have 3 seconds. So we would be doing there 3 seconds being multiplied by 18 degrees per second. And that would be 30 plus 24, which would be 54 degrees. And we'd basically be able to draw that 54 degree angle on our, in green right there. But then the same thing we'd be working on. We'd be working on the same kind of right triangle, where in this case, you kind of see a little picture of it down here. So we'd have the 25, that's the constant. We have 54 degrees, and then x. So the same thing would happen here. We would still be doing the sine of now 54 equal to x over 25, and x would equal 25 sine of 54. So you can see how similar that is, and we would just be similar to before, doing 30 plus 25 sine of 54 degrees, and that would equal, as an answer, 50.2 feet off the ground. So we've done all of the first quadrant heights, and you might have started to see a pattern that are for our inputs for sine. So up here we did 18 degrees per second times 1 second up at the top there. Then we did 2.5 times 18. So that would have been, instead of 45, we could have done 18 times our number of seconds. And then the 54, that was 18 times 3, which was the number of seconds. And then the 30 and the 25 and the sine were exactly the same as they were before. So that means that for our first quadrant, so anywhere between 0 and 5 seconds, we could use the equation 30 plus the sine of 18 times how many seconds we used, because it was 18 degrees per second times the number of seconds gave us the angle we needed in all these examples. And that would equal our height. So we found an equation that works for anything between 0 and 5 degrees. So now we're going to look at, well, what happens if we're in the second, third, or fourth quadrant to kind of wrap up this video now. So in order to do that, we need to look at, well, where we'd end up for some of these values. So if we grab our paper from earlier again, we can see on our Ferris wheel that we marked that our second quadrant was between 5 and 10 seconds. So if we look for between 5 and 10 seconds, well, we have 6 seconds and 8 seconds to choose from. So let's look at 6 seconds first. So we can draw our Ferris wheel, and point A is where we're starting again. So if we are going to be looking at t equals 6 seconds, well, we are doing 18 degrees per second times 6 seconds again. So that would be 6 times 18 equaling 108 degrees into the circle. So 108 degrees would be somewhere kind of just past 90, somewhere maybe along that region. So that red point right there, that is 108 degrees. Now, that might kind of ring strange to you watching this video because we've only really done trig with mostly angles that are less than 90 degrees. So because that for right triangles, there's no right triangles with 108 degree angles. So we need to figure out, think back to what we did before in prior videos. So when we were on the left side of our Ferris wheel, we had a kind of a line over here to the left, and we had a height in x right here that we'd be adding. So we would just need to figure out what this angle is instead and use that for this little right triangle that I just made right there. If I know that half of a circle is 180 degrees, I can do 180 degrees minus 108 degrees, and that gives me an angle to use that would be 72 degrees. So if I have that little triangle where I have a 72 degree angle, x, and my radius is still 25, well, I can use that to solve for x. I would just need to use sine of now 74, and then that would equal to x over 25. So I would get an answer of 25 times the 74, or 25 sine of 74 is equal to x. And then, so if I know that, well, I'm just doing 30 plus sine of 74, and that would equal my answer for the height. 30 plus the sine of, we missing the 25. Let's rewrite that. 30 plus 25 sine of 74 gives us the height. And 30 plus 25 sine of 74 is equal to 54.03 feet. So that 74, we got the 108, remember, from doing 18 times 6. That kind of looks similar to what we did before. So what the difference was, we had to do 180 degrees to kind of go backwards from the half circle to get the 72 degrees. So we could use the right triangle trig that we all already know. Now, if I'm doing this with other angles, I can do the same thing. Like I could apply this to 8 seconds instead, which is going to be my second quadrant as well. So if I just use my equation right there, I could do basically a combination where I'm going to combine this part and this part. So I would know I would be doing first, I'd be doing 8 multiplied by 18. And then I would just subtract that value from 180. So as I know that the angle I would have after 8 seconds would be 144 degrees. But if I go backwards from 180, I would have an angle of 36 degrees. So now I can use the numbers I was using before. And so that means that my equation is going to be 30 plus 25 sine of what I just did. 180 degrees minus 18 degrees per second times 8 seconds. Or in other terms, 30 plus 25 sine, and that ends up equaling, I think I said it already, equals 36 degrees. And so we have an answer there that is basically the same as our 36-degree angle we did before already, which ends up being about 44. Let's check it. 30 plus 25 sine of 36 equals 44.7. And so we can now kind of apply that to more parts around the circle. We can look at, well, if our number of seconds, if we're going 18 degrees per second around the Ferris wheel, we can apply that to the rest of our numbers around the circle. Because if we go past our numbers, we can just keep applying this. So if we're thinking about our third quadrant next, we would then kind of think about numbers like, let's grab our page again that we used our key on earlier. So we knew that between 10 and 15 seconds was our third quadrant. So let's pick one for that one to try. So now with our third quadrant, we have our Ferris wheel in point A. So our third quadrant, we could say 14 and a half seconds. So 14.5 seconds. We multiply by 18 degrees per second. And that means we'd be a total of 261 degrees around the circle. So if we drew that on here, so 3/4 of a circle is 270. So we'd be just short of that down here. So we'd go all the way around like that. Now, we can't put 261 degrees into our knowledge that we have so far of sine, because that wouldn't fit in a right triangle, since it's almost 3/4 of a circle, a very large angle. But what we can do is think about how far past 180 degrees we went. So if that is the case, we would be doing 261. If we take away 180, that would leave us with the angle in green that we might want, or in red, we'll say, right here. So if I do 261 degrees minus 180 degrees, that looks like 81 degrees. So we have an 81 degree angle, and we have x, and we have 25. So basically what we just did there was our 18 degrees per second times 14 and a half seconds minus 180 degrees. So we can now apply our rule from before to what we were kind of doing now. So we're still doing now, since we have 30 feet is kind of out here, we would be doing 30 feet minus what you get as an answer. So different from before, now we are doing 30 feet minus 25 sine, just like we've been doing every other time. But now we have our 18 times 14 and a half minus 180 gives us the 81 degrees we'd use over here. And remember, what we were doing over there was sine of 81 is equal to x over 25. And then you would get 25 sine of 81 equal to x. And from lesson yesterday, we did 30 minus 25 sine of 81. And that would give us that x value, which that x value equals 30 minus 25 sine of 81. That equals 5.3. So pretty close to the ground, as you can see in our picture, pretty close to the bottom of our Ferris wheel. And so our function right here for when t is between 10 and 15 seconds. Well, that means we just need to do our angle that we're going through, 18 degrees per second times number of seconds, but just take away half a circle to go back to kind of think about it in terms of our first quadrant. So we would be getting our final answer by just doing 30 minus 25 sine, and this all equals the 81 we just used, and our answer was, we already got, was 5.3 feet. So we have answers from before. For the first quadrant, we did 30 plus 25 sine, and then 18 times t. And then after that, we did our second quadrant, which we are doing here. We did 180 minus that. So that equation would end up being 30 plus 25 sine. And we did 180 minus seconds times 18. So 180 degrees minus 18 degrees per second times the number of seconds gives us our height. And that is for when t is from 5 to 10. And now to wrap things up in our last couple minutes of this video, if we are in our last quadrant, that is between 15 and 20 seconds. So between 15 and 20 seconds, let's go with 18 seconds. So if we do 18 degrees per second times 18 seconds, 18 times 18 would be 324 total degrees. And so if we draw our circle here, and our A value that we're always starting from, 324 degrees would be just short of 360 degrees. So it would be down here. So in order to get an angle that's less than 90, all you need to do is, well, this went all the way around the circle. So we just need to figure out what this angle is right here in order to get this x value, which would be 30 minus that x value. So if we wanted to get that x, we would have to just do 360 degrees minus 18 times 18, and that ends up being equal to 36 degrees, similar to earlier. So our equation for this last quadrant ends up being 30 feet minus the 25 sine, and now just instead, we're doing 36 minus 18 times 18 seconds. So 30 minus 25 sine of 360 minus 18 times 18. And that's about 15.3 feet off the ground. So that kind of concludes our video right there. And just remember that when we were doing 18 seconds, we got all the way around. So we'd have a total of 324 degrees. And so if you kind of think about it, there'd be 36 degrees left. And that's how we knew that this angle right there was 36 degrees. And then we were solving for x in the same way we've been doing so far. And so we had basically to figure out, as a reminder, that we were doing sine of 36 equal to x over 25. And that kind of led us there. So just remember, we're using the 360 minus 18 times the number of seconds to get this 36 degree angle, because we only want to use degrees and angles that are between 0 and 90 so we can relate it to a right triangle trig problem that we're all more used to. And so the general equation here would be 30 minus 25 sine of 360 degrees minus 18 times t. And that would end up giving us the answer that we got before of 15.3. And that is our height. And that was for when we were between 15 and 20 seconds. So you can apply that to basically any amount of degrees or seconds around the circle so that you could find your height after more than one rotation, after more than 20 seconds. And so we will finish our video there. And that basically covers how we can use an equation to represent the height you are off the ground in going around a Ferris wheel. And that concludes our video for today. Thank you for watching.